start. We have main engine start. 4, 3, 2, 1, 0, and liftoff. The liftoff of the space.
In our natural pursuit of knowledge, space has always mystified and beguiled us. Over the past 5 decades, we've pushed the final frontier inevitably onward into the ether. The cost has been colossal. Now every day, new data, new conclusions, and the thirst for deeper exploration propel us inexorably onward. The advantages of the discoveries made through space travel are myriad, but the fundamental curiosity as to what is out there will always fascinate and taunt us. Come with us now into the unknown and discover the disappearing frontier. In this edition, we look at the International Space Station and the tasks that will beset the men and women who will soon be living and working on this orbiting marvel. You'll see Ulysses and how it used the gravity of Jupiter to bend its flight path on its mission to study the Sun and the solar atmosphere expanding into space. And through the brilliance of a sophisticated radar instrument on board the Magellan spacecraft, we're able to take you on an unprecedented flight over Venus. Those stories coming right now. 40 years ago, we trained our eyes toward the stars as the first humans orbited the Earth. In the 70s, we looked up again to the heavens and saw humans actually working and living in orbit, and witnessed cooperation in space by bitter adversaries. By the early 1980s, the space shuttle was streaking toward orbit in the name of technology and discovery. The 90s will be remembered as the beginning of an era of space exploration, the development of the International Space Station. The world's largest laboratory in space will support scientific and technical research performed on Earth by taking advantage of the unique environment of space. This orbiting complex will remain aloft for up to 15 years and will allow scientists to accelerate the rate of discovery and invention for practical applications in health, medicine, materials and technology. Researchers will use the International Space Station to conduct experiments in 5 scientific areas. Research in biotechnology will enhance our ability to accurately characterize human proteins, enzymes and viruses at the molecular level by studying protein crystals grown in microgravity. Scientists may then develop better medicines to fight against AIDS, cancer, diabetes, and many other diseases. The International Space Station also opens another window onto the human body's adaptation to a gravity-free environment. Exposure to microgravity can cause an otherwise healthy astronaut to experience rapid loss of bone mass comparable to osteoporosis, but at a much faster rate. Until now, on-orbit research for US investigators in this field was limited to short-duration flights on the shuttle. Now, extended investigations on the station offer new insights into the aging process. Fluid physics research will utilize microgravity to examine the behavior of liquids, gases, and mixtures. Private industry will use the results of these studies on the behavior of fluids in the absence of gravity to design more efficient production processes. Agriculture can also benefit from space station research. Biologists have long studied gravity's influence on living organisms. On the shuttle, scientists have performed studies subjecting both plants and animals to the sometimes adverse effects of weightlessness. On the station, this type of work would expand the fundamental knowledge that could benefit reproductive life cycles. This level of space-based research could one day lead to heightened produce harvest. By allowing farmers to reduce growing cycles, thereby increasing crop yields. Experiments in other fields of study will seek advances that could improve technology in communications, computers, consumer electronics, energy efficiency, glass and ceramics, and metals manufacturing here on Earth. Science will be performed by a multinational crew of astronauts, cosmonauts, and researchers. They will live and work on the station for up to 6 months at a time. The atmosphere inside the station is pressurized to a sea level pressure of 14.7 pounds per square inch, providing a comfortable living environment for crew members and an optimum operating environment for science research. The station is comprised of numerous interlocking components that are assembled on orbit one segment at a time. The station will be made up of 7 laboratories, living and sleeping quarters, life support systems, energy generators, modules for propulsion and attitude control, and other essential systems for navigation and communications. Building the space complex is a partnership of nations spanning the globe. Each contributes resources and scientific expertise based on technical knowledge, capability, and national interests. The ground-based construction of the space station hardware began in the United States with the development of connecting nodules or hubs called nodes. Later, halfway around the world, manufacturing began on the first building block for the world's largest space science platform, the Functional Cargo Block, better known by its Russian acronym, the FGB. This space vehicle, built by the Russians for the US, provides power and propulsion in the early months of on-orbit space station construction. The Russian Space Agency plans to contribute to the station a complex vehicle known as the service module. Complete with living quarters, propulsion and navigation, as well as room for science experiments, Russia will also provide 3 smaller research vessels and an energy tower to augment the power capability of the station. Other elements being manufactured by NASA and its contractors are a laboratory module that can house close to 100 science experiments, living quarters for the crew members in the habitation module, and an airlock to allow for spacewalking tasks. The long truss structure supporting the space station's power-producing solar arrays is the backbone of the orbital outpost. The complete station structure will have a wingspan of 356 feet, longer than a football field. A robotic arm that runs the length of the truss to maneuver humans and hardware around the station is being built by the Canadian Space Agency. Agility of the arm is expanded through the use of a human-like robot, a smaller robotic extension that gives the astronauts a hand in conducting delicate work outside the space station. Another laboratory with numerous science experiments located both inside and outside the station is the Japanese pressurized module and its attached exposed facility. This exterior pallet allows astronauts to move experiments from the safety of the experiment module to the harsh environment of space. On top of Japan's laboratory is a smaller component that's used to store and resupply experiments. A smaller research module, built by the European Space Agency, offers yet another venue for scientists all over the world to see their life's work come to fruition on orbit. ASI, the Italian Space Agency, is building resupply vessels called mini-pressurized logistics modules, which will be flown to the station aboard the shuttle 4 times a year. These modules will hold food, equipment, and new experiments to be located in the station's various laboratories. Constructing space vehicles on the ground, then attaching them on orbit, will help each partner nation to learn more about how to build, maintain, and operate large structures in space. Hauling hardware into orbit for the assembly of the space station requires 43 space flights on 3 different types of launch vehicles: the US Space Shuttle, the Russian Proton Booster rocket, and the Russian-built Soyuz booster. Once it's complete, the station will weigh over 1 million pounds and will be positioned in an orbit 220 miles above the Earth. The International Space Station will circle the planet every 90 minutes, traveling at a speed of 5 miles per second. Its orbit will be inclined 51.6 degrees to the equator, allowing the complex to travel over 85% of the Earth's surface every day. From this extraordinary vantage point, scientists will be able to conduct long-duration research on our planet's environment, its natural resources, as well as its atmospheric and oceanic conditions. This sprawling space campus will be controlled from both the Russian Mission Control Center outside of Moscow and Mission Control at Johnson Space Center in Houston, Texas. As components from other partner nations reach orbit, a direct communications link will be established with each nation's Space Operations Center, providing a more effective means of interaction with science and research investigators in those countries. As early as this year, the International Space Station expects to support the work of more than 1,000 scientists at universities and laboratories all over the world. Some researchers will have the opportunity to monitor their experiments as they're being conducted and communicate directly with the astronauts operating the experiment. For the first time ever, long-duration spaceflight is available to an unprecedented number of scientists and engineers looking for answers to age-old questions. An orbiting laboratory virtually free of gravity will result in new insights and knowledge in scientific and technical fields in ways that can't be achieved on Earth. Research on the ISS could touch the lives of almost everyone who is invested in this technology marvel. For the price of one night at the movies each year, the space station will become a symbol of the investment in our future, a visible light in the sky for our children to look up at and dream about the wonder of space travel. 4 decades after humans caught their first glimpse of Earth and the heavens from orbit, the ISS becomes a permanent home in space to enable those with a curiosity to explore and those with an unquenchable thirst for knowledge to answer questions yet to be asked about our planet and the universe. In June 1994, the Ulysses spacecraft began an expedition over the poles of the Sun. Its mission is to study the Sun and the solar atmosphere expanding into space. Little is known about this star at the center of our solar system, yet it dominates all life on Earth. To reach the high solar latitudes never before explored, the spacecraft used the gravity of an immense planet, Jupiter, to bend its flight path out of the plane in which the planets orbit. Looping back inwards towards the Sun, the spacecraft would then journey onto the Sun's southern pole. Ulysses was launched on October 6, 1990, aboard the Space Shuttle Discovery. Nine experiments would study the solar wind and energetic particles streaming outward from the Sun's corona. The experiments would also study cosmic rays entering the solar system from interstellar space. 16 months and 575 million miles after launch, the spacecraft began these investigations after its arrival at Jupiter. Closest approach occurred on February 8, 1992. The experiments would be used to study the region dominated by the rotating magnetic fields of Jupiter, called the magnetosphere. Particles trapped within Jupiter's magnetosphere comes from 3 sources: the solar wind, Jupiter's upper atmosphere, and Jupiter's moons. One of Jupiter's moons, Io, contributes to the Jovian magnetosphere at a rate of nearly 1 ton per second. This gas becomes ionized and forms a ring called a plasma torus that circles the planet. Ulysses will measure the composition of this donut-shaped plasma ring. At greater distances, a rotating sheet of plasma encircles Jupiter. Centrifugal force slowly drives gas in the plasma sheet outward until it eventually escapes from Jupiter. Outside Jupiter's magnetosphere is the solar wind. This wind blows at speeds of about 1 million miles per hour. The wind can't penetrate the Jovian magnetosphere, but is deflected around it. Ulysses' predecessors, the Pioneer and Voyager spacecraft, entered the Jovian magnetosphere when the local time was near noon and exited in the pre-dawn region of the planet. The Ulysses spacecraft followed a path similar to its predecessors as it entered, but left on the dusk side of the planet. During its 10-day tour of the Jovian system, Ulysses performed experiments and explored regions of the magnetosphere not visited by the other spacecraft. From there, Ulysses would be on its way to explore the poles of the Sun. Venus, the brightest star in the evening sky, has captured our imagination for centuries. Its thick, swirling clouds have never allowed a camera or a telescope to glimpse the surface below. Since August of 1990, though, a spacecraft named Magellan has peered beneath this veil of mystery to show us the surface of Venus in unsurpassed detail. The secret of Magellan's success is a sophisticated radar instrument that operates with incredible speed and efficiency. During a burst of activity that lasts less than a second, Magellan acquires imaging, altimetry and radiometry data. This information is used to make images of the Venusian terrain, to determine the height of surface features, and to measure the microwave energy that is naturally emitted from the planet. Magellan gathers data for approximately 25 minutes during each 3-hour orbit around the slowly turning planet. Starting at the North Pole and moving south, Magellan maps strips that are about 16 miles wide and nearly 7,000 miles long. Twice during each orbit, Magellan turns its dish antenna towards Earth and transmits the data it has just acquired. While this happens, engineers on Earth trap the changing motions of the spacecraft to learn about Venus's gravitational field. The large antennas of NASA's Deep Space Network receive the stream of data from Magellan, then transfer it to NASA's Jet Propulsion Laboratory. Computers process the data into 15-foot-long image strips. These strips provide the first look at what Magellan has discovered. Additional processing of the strips reveals exciting and sometimes puzzling details. A massive lava flow that appears to come from the rim of an impact crater. A 4,000-mile lava channel that is unequaled in the inner solar system. And an unexplained jet-like streak associated with another impact crater. Computer technology combined with altimetry data enables us to take a simulated flight over the planet. We start at 3 impact craters, the largest approximately 40 miles or 60 kilometers across. The bright rim was created from debris that was thrown out when meteorites hit the surface. Moving southeast, we pause to observe a small volcanic caldera, then rise to focus on Alpha Regio, a highland region in the southern hemisphere that spans 800 miles. The circular feature at lower left is a corona. These features are found only on Venus and are thought to be volcanic in nature. Now we descend for a closer look at the complex terrain of Alpha Regio. Our path then zooms east over jagged reaches to a volcano with a fluted rim, unofficially called the Tick. Our journey through Alpha Regio continues over hundreds of miles of rugged territory. Turning northeast, we leave this tortured area and to 7 pancake-shaped domes. These volcanic eruptions rise up to half a mile above the surface and average 15 miles across. They may be made of thick, sticky lava. Such domes have only been seen on Venus. Our flight then continues to the west and ends near the rim of an impact crater. The colour used here is from a photograph taken from a Soviet probe that landed on the surface of Venus in 1981. Straight ahead is Sif Mons, a volcano that towers more than a mile above the surface of Venus. As we approach its sprawling base and climb to slowly circle the peak, many lava flows and other scars reveal the volcano's violent past. We turn south to look at another crater. Then a quick flight to the east brings us to the mouth of an extraordinary 600-mile-long rift valley. We arrive at another volcano named Gulao. Here we skim its mile-high summit and descend to view the lava flows and rigid terrain of its northwestern face. A volcanic caldera now in sight is further evidence of Venus's active geologic history. We now turn east and follow a dark streak of unknown origin that leads to 2 impact craters and a lava flow that has travelled many miles from its source. Looking northeast, we ascend for a panoramic view of the area just explored, the western portion of Isla Regio, an elevated zone in Venus's northern hemisphere. The last part of our trip takes us over Artemis, a broad sweeping canyon that is of great interest for geology and geophysics. This canyon is so beautiful that it would be a tourist attraction if it were on Earth. An important strategy for the extended mission was to change the angle of the spacecraft so Magellan could record a different view of the surface. Will Magellan's multiple observations of Venus reveal changes in the surface features? Is Venus, like Earth, still an active planet? These and many other questions about this intriguing planet are likely to be answered as current and future generations of scientists analyze the data provided by the Magellan mission. Venus is often called Earth's sister planet because they're so similar in size, mass, and distance from the Sun. What Magellan teaches us about Venus will undoubtedly help us to understand the similarities and differences about all the members of our solar family.